This is physics lab number 6. This is magnetic molasses by Jackson Pagan. So some introduction. The main purpose of this lab is to actually see physically the forces from magnetic fields when there are changing magnetic fields. And so what we did in this lab is we took a tube and we wrapped aluminum foil around it. And this aluminum foil is conductive so that when it basically creates a lot of rings. Um, and when a magnet falls through that, it will experience forces from the rings as well as the forces from gravity. And we observed that as it falls through the tube, it falls at a normal speed before the tube, but as it enters the tube, it slows down very clearly and takes a lot longer to come out of the tube. So, we also then take code and we will um, calculate out a time that it would take to fall through the tube and then compare that to what actually we saw. So our average actual time was 1.16 seconds. Our simulated time was 1.08. It's pretty close to the actual time. And some background equations, we're going to use Faraday's law, and we're also going to use Ohm's law and the equation for force. So these are all shown here. We also have a more specific equation that we're using on the bottom for the change in flux. So here's a visual model. You can see that as the magnet falls, there's a force exerted on the ring, um, or there's a magnetic field exerted on the ring. And as the magnetic field changes, it produces a current, and the ring itself will also exert a force onto the magnet as it falls through. And so our experimental procedure here was we marked the North Pole, we measured the mass, we find the width of the foil, width of the inner tube, and the length of the tube, and then we would drop the magnet into the tube 5 times, take the average of those times, and then we would, after that, we would use Python to create a model of the magnet and the tube interaction, and then get a time from that as well. And some of our observational results, the average time through the tube was 1.16 seconds, like the 2.46, width 0.005, inner radius, etc. So here's our computational model. We have our constants at the top. And then we have the measurements that we took on the bottom of that left one. And then our mass of the magnet, and we have mu there as well. And so this was on the top left, the function we used to actually calculate the dipole moment or not, the magnetic field. And then after that, we calculated magnetic flux on the bottom left. And then we set up our forces, the force of gravity and the force from the magnet on the right. And then we take our net force on the very bottom on the right. And then our results, this is our graph. We can see like as it enters the tube, it will speed up very quickly. And then once it gets into the tube, it actually stays at the same velocity all the way through the tube until it hits the very bottom. As it comes out, it'll speed up again. So our experimental time was 1.008 seconds. This is pretty close. In the model, as the magnet falls, there is a blue ring above it and a red ring below. And so blue is clockwise because it pushes the magnet down, while red pushes it up, so that'd be counterclockwise. The dynamics of the system when you flip the magnet, they shouldn't change. It's just about the movement of the magnetic field, not the actual direction of it. And then how does it total time in tube of real world system compared to that of your computational system? It's pretty close, off by 0.07 seconds. Probably didn't factor in the time of, we may have had some errors with when like starting the timer before it enters the tube, that kind of stuff. And then shape versus velocity time, it shows the magnet enters the damping force quickly ramp up as it goes into the tube and hold steady until the magnet falls out. And then the resistivity of the conductor was 0. This is a superconductor, and it would not go into the tube. The forces would equal out, and it would just float above the tube, ideally. And then if holes were cut into the tube, they wouldn't be full loops anymore, and the forces would be much, much smaller, and it would probably fall at a normal rate. And